Good morning, everybody. This is Keely Brooks. I work for Southern Nevada Water Authority. Before we get started, I'm going to walk you through some housekeeping items before we launch the actual show. So right now you see this is a screen of the attendee interface. And to the left is the GoToWebinar viewer where you will see the presentation. And then to the right is the GoToWebinar control panel where you can ask questions and select the audio mode. So you can choose to listen through your computer speaker system or over the phone. If you're joining over the phone, select phone call in the audio pane and dial-in information will be displayed. You can submit text questions by typing your questions into the chat pane of the control panel. You may also send your questions at any time during the presentation, and we'll address them as time allows during the Q&A session at the end of the presentations. Each presentation will last about 15 minutes, and questions will be responded to at the conclusion of all 5 presentations. And we'll get started in just a minute.
Yeah, all right. Thanks, Keely. Really appreciate you going over that housekeeping stuff and, of course, all of the hard work you put in to get us to this point. Thank you so much. So I just want to welcome everyone to our 2020 Colorado River Hydrology Research Symposium webinar series. My name is Seth Shanahan. I am the Colorado River Programs Manager for the Southern Nevada Water Authority. Today's webinar is one of 3 webinars, and it's entitled New Models and Data to Inform the River Forecast Center Water Supply Forecast. It's hosted by SNWA and our partners from the Colorado River Climate and Hydrology Work Group. Next slide. So I just want to introduce folks to the Climate and Hydrology Work Group if you're unfamiliar with us. We've been meeting for a few years now, and we have a volunteer group of representatives across the Colorado River Basin, mostly from state agencies, state and local water agencies, as well as large water utilities, and of course our federal partners at the Bureau of Reclamation, the Colorado Basin River Forecast Center, and at NASA. Now this group has a 3-part goal, and I'm just going to explain what those parts are real quick. The first is to advance scientific understanding to improve the accuracy of hydrologic forecasts and projections. Second part is to enhance the performance of predictive tools. And the third part is to better understand the uncertainty related to future supply and demand conditions in the Colorado River Basin. Next slide. So this work group has been pursuing a research agenda for the last few years to try to meet that goal and have invested approximately $1.5 million in various activities out in the basin. One of the first activities that the group decided to pursue was something that many of you probably are familiar with, and that is the State of the Science report released back in April of this year by Western Water Assessment. Now, our work group recognized that to manage the Colorado River Basin in a sustainable, responsible, and essentially good way, we need to all understand the science information that is out in the landscape. And it had been quite a few years since a compendium of information had been prepared on these topics. And so we recognized and pursued in partnership with Western Water Assessment the development of the State of the Science report. And it's really in this document that we're trying to lay the foundation of a common set of facts, information about what we know in the basin that we can use as essentially water users to try to make better decisions, but then also to have the entire research community in the Colorado River Basin understand as well what we do know, what we don't know, and where are there opportunities for us to explore future topics. So want to thank many folks who are on this call that I see popping up who actually helped write this document or review parts of it. It's really this community of people that helped make this document as helpful as it is to us. Now, of course, this document can't provide every answer or every topic addressed in all the ways that we might want forever and ever. It's a living document. And there are many topics that our webinar series is going to be addressing that the State of the Science report couldn't in some ways, or simply wasn't the right timing. But what's really helpful in this document is that there is a listing of various challenges and opportunities in the basin in regards to the climate and hydrology science that we know. And so really this webinar today and the next two coming up are explorations of some of those challenges and opportunities that were identified in the State of the Science report. Next slide. So with that, I'd actually like to introduce our moderator for today's set of presentations, and that's Sarah Baker. Sarah is a water resource engineer with the Bureau of Reclamation's Lower Colorado region. She received her PhD at UC Boulder with an emphasis on climate forecasting applications and water management. And at Reclamation, she focuses on streamflow forecasting and modeling of mid to long-term water management in the basin. So thank you, Sarah, and it's all yours.
Thanks, Seth. So here's today's agenda. We have 5 different presentations. We will first hear about subseasonal to seasonal outlooks for hydrology from Matthew Rosencrantz, followed by Mackenzie Skiles with incorporating remote sensing and snow energy balance modeling in runoff forecasting in snow-dominated watersheds in the Colorado River Basin. Andy Wood will then discuss a new hydrometeorological modeling resource for U.S. water resources applications. Sean Fleming will provide an introduction to the new NRCS water supply forecast platform for the U.S. West, a meta-system blending AI, geophysical knowledge, multimodal interference, and practical requirements. Lindsay Barrett will wrap up the presentations by discussing merging of high-resolution airborne snowpack data with existing long-term hydrometeorological observations to improve water supply forecasting. So throughout the presentations, please remember to enter any questions you may have in the chat box. Our first presenter is Matthew Rosencrantz. Mr. Matthew Rosencrantz is the director of NOAA's Climate Testbed, focused on transitioning innovative research to NOAA's operations at the Climate Prediction Center and Environmental Modeling Center. Prior to that, Matt was the CPC's lead forecaster, making and improving outlooks for climate extremes, including drought, tropical cyclones, and heavy precipitation events. Before coming to NOAA and the National Weather Service, Matt was a weather officer for the United States Air Force. Mr. Rosencrantz's presentation, titled Subseasonal to Seasonal Outlooks for Hydrology, will address bringing climate prediction into NOAA's RFC streamflow forecasting workflows, which is one of the opportunities presented in the State of the Science report. I'll now hand it over to Matt for his presentation.
Good morning, everybody. Or yeah, still no afternoon for the East Coast folks, if anyone's on. We are focusing on achieving that science goal, getting subseasonal to seasonal outlooks for water supply through to the RFCs. Also, this project is kind of rolled into the USGS as well. They've come into the project, so it's a little bit expanded beyond just the RFCs. But we've also been able to integrate in some other aspects of NOAA, such as Physical Sciences Laboratory and the Office of Water Prediction. So we can go next slide. So I'm going to talk about background, members, some goals, what we've done in fiscal year 20 and what we're planning to achieve in fiscal year 21. For those not for the federal government, fiscal years run 1 October to 30 September. So we all know water is precious, and we want to constantly improve how we manage it. about 2 years ago, myself, the director of the Climate Prediction Center, Dave Dewitt, went out and visited the 3 major river forecast centers in the West, including one in the Colorado Basin, where we had a lot of in-depth discussions on what are the needs for modeling the water supply and modern hydrologic modeling. One of the big things we came up with is that the ensemble prediction system, ensemble streamflow prediction, and the HEF system that they use they're forced with the precipitation and temperature data that goes into them is observation based, and then the model based portion of that is out through about 10 days. Depending on the scenario. In their experiments, they run experiments out to 15 days. And then after that, it goes to climatology. So what we thought about is, well, Climate Prediction Center's forecast products being developed at the Physical Science Laboratory in Boulder. They show skill above climatology. So if we can give them a more skillful starting point, the hope is that we end up with a more skillful forecast for runoff and water supply. I also came into the knowledge that there's other hydrologic modeling efforts that use no projected forcings. They just use up through the observations. So I wanted to make sure that groups that are out there that are familiar can potentially tap into that, to our predicted state of the atmosphere to potentially force other hydrologic models. So next slide. So we have a few different methods at CPC, as well as with NOAA Physical Sciences Laboratory, to make forecasts for week 2 and beyond. So how do we get to where we're forcing or giving information out? So for the ensemble streamflow prediction, that has 90 days of precipitation in there, actual precipitation forecasts that over long histories are shown to be more skillful than climatology. Can we get to them? So we're first starting with our week 2 forecasts, which we have kind of known public forecasts. That's the top image on the right there. And the skill of that is the top image on the left. The thin black line is the 0 line, and our long-term skill is well above that 0. So can we make forecasts through day 15 and get them into the river forecast center's computing systems, and then use that as a model to extend out further into weeks 3 and 4. So that way they have data all the way from day 0 all the way out through day 28 of temperature, precipitation, snowfall, whatever kind of physical parameter they would need to force their model. Bottom right image, so on the left-hand side, the bottom right image is an example of something from Physical Sciences Laboratory that they are also working to fit their methods into the river forecast centers. And if that's proven to be a more successful method, then Climate Prediction Center could onboard that and make sure it's routinely and operationally available to the river forecast centers. Next slide. So this is the current team members. I'm not going to spend too much time on this slide, but team from CPC, Office of Water Prediction, Weather Service Headquarters, all the RFCs out west, Physical Science Laboratory, and then as well as one of our other members here, Seth. Next slide. So one of the project goals, I know it's a lot of words in the slide here, but within the Weather Service, we are really tailoring our model output to fit into the RFC models. And we're going to work with them to further refine how they use climatologies further out in time, further than we might be comfortable providing model data to. And then we're also going to work on refining our model output, so that tailored model output, even refining that further, should there be any scientific developments as far as statistical methods, or as models are upgraded in the Weather Service and their operational computing, continuing to be able to basically keep that pipeline to the river forecast centers, keep that wide open and flowing. Physical Sciences Laboratory, they are working on a lot of different calibration methods, and one of the big current methods they're working on is creating ensemble members across forecast time. So it's using an ensemble copula coupling. That's the method they're using. And what it does is it creates synthetic members from the atmosphere for temperature and precipitation that are both consistent across each other. Sometimes if you work with just precipitation data or just temperature data, you can do calibrations and downscaling on them, and then they become inconsistent with each other. But ensemble copular coupling is a way to make sure that they're consistent with each other, and as well as consistent from time period, from the start of your forecast to the end of your forecast. And then they have pledged to keep working this year to even refine whatever value added they came up with in fiscal year 20 to do some next iterations on that. Again, we're also working with the USGS modeling team to provide similar types of information to their modeling team. So next slide. One of the things we did was CPC, Climate Prediction Center, we have access to a lot of NOAA's model runs that go backwards and that are looking back in time. So we took this all the way back to 1985, all the way up through 2018. I know the x-axis is up there because it depends. One of the things we do is we run comparisons between the historical model runs and the observations. And then we figure out how good the model did or did not do in the past, and we use it to calibrate the current forecast. So then we run the real-time forecast from NOAA through these calibration statistics, and we get to a value added. That's one of the things that a lot of organizations that calibrate models, we do this every day. There's a couple of links in this PowerPoint. And CPC and the Physical Sciences Lab, we've been doing this for a long time. 1998 model run was one of the first times we really did started this. So over 20 years of kind of doing model calibrations like this in this fashion. Before that, it was current model runs versus observations, so a little different. It wasn't such big data sets. Physical Science Laboratory has developed improved methods, again, to restore that how the model members across space and time, how precipitation and temperature, how they link together. After you correct each one, you then kind of compare them to each other and make sure that they are consistent. And then we're working on combining multi-models. So we've all seen the plots for hurricanes where here's the US model, here's the Euro model, here's even Japan has a model, Canada has a model. How can you combine all of them in a way that gives a little bit more accurate assessment of what might happen in the future? So next slide. One of the things we've done here for initially was we took all of the obs and the observations from the years and the reforecast. But the River Forecast Centers said, well, we want a history of how would your value added product, our CPC calibrations, how would that perform if we had it in 1985? So then we said, okay, how can we do that? So we went back and recreated our value added product for those 30 years. And they're evaluating it right now at the Colorado Basin, California, Nevada, and Northwest. Next slide. So that's basically what this first bullet in the slide describes. We've done it for precipitation. We are working on it right now. The codes are running right now to provide it in for max and min temperature. We're also reprocessing European Center data and hindcasts down to 6 hourly. We're just right now working on different methods to transfer it. European Center is working on getting to an open data model like the US is, but right now it's still proprietary. We're also working on the results from last year's forecast rodeo that some people on this are familiar with, the winning team. We are running them on our compute and testing them for potential implementation here. So what I wanted to really highlight on this slide is we're not really beholden to a single method. We're beholden to what makes the most accurate precipitation forecast and temperature forecasts and whatever relevant parameter it is. So we're not beholden to a method. Whatever gets the most accurate information out there, let's get it. Next slide. Physical Science Laboratory. They are working on different methods. They're post-processing their precipitation and temperature files. They're also working on developing freezing level forecasts. That was highlighted as something that was very important. So that's something that Climate Prediction Center hasn't done in the past and doesn't really have a lot of expertise in. So it's more developmental, and that's where our laboratory will be working on it. And again, their methods are, you can see from the top panel to the bottom panel. The top panel has forecasts, 11 members from the hindcast, but when they post-process it, and then they can add synthetic members by blending across time, so the members are consistent in a spatial and temporal way. They're consistent across the variables and across time, so you don't have a huge chunk of precipitation in the beginning that isn't consistent with your total at the end. And you can do that and combine these members out of those 11, you can recombine them and make up to 33 members. So that allows you to more accurately gauge potential for high events, or potential for low flows, potential for cold snaps or warm periods much better. Next slide. That's fine. They're also doing some statistical post-processing. I know this is for mostly for California. They've really done a lot of different periods of accumulation to figure out 6-hour periods of accumulation. But how can you really break down long-term forecasts into smaller time periods? And then, so they've come up with a couple different post-processing methods. And the system they have allows them to intercompare the methods. And then intercompare the resulting stream flow predictions to kind of optimize their post-processing. So again, how do you really create forecasts that are really optimized? Next slide. So this is what the RFCs we're working on. So they're getting all this data delivered, and they are bringing either CPC or PSL products through MEFP. They're running HEFs on their HES basins, and they're going to results will inform in a few ways. Is the disaggregation methods that we've chosen, because a lot of times when you make seasonal and weekly forecasts, you do forecasts that are a week long or 2 weeks. How do you break that down into hourly forecasts or 6-hourly forecasts? Could we also look at just daily forecasts rather than 6-hour forecasts? So, and you can see their goals in the bottom. They really want to evaluate the skill of the hydro models with the new forcings from CPC or from PSL. And we really want to establish a really good framework and a pipeline for which we can continually feed and test new methods. Next slide. Fiscal year 21, I'll go through this pretty quick because I think I'm running up on time. So next slide. One of the things we want to do is multi-model calibrations. So if you look in the bottom left, we can, off the US model, the Global Ensemble Forecast System, the value added product for there. We can combine the European centers. We can combine lots of other models we have access to. I mean, these data sets are really big. They're multiple, 20 or 30 terabytes, some of these old long data sets. So how do you optimize them and use them in the right way? The bottom row there is what CPC currently does for our forecasts. So where we combine all the value added forecasts versus recent observations, come up with a weighting scheme, and then you apply that and that goes out the door as part of our forecast for the day. If we go to the next slide. How could we do that over time, and how could we add in any model we wanted? So that's why there's that mod X in the bottom left there. As new models are developed and new models are made available, how can we bring them in a flexible system that can provide the best estimates to the river forecast centers? Next slide. Some of the planned activities are creating that historical multi-model blend, like I just talked about. How do we create the multi-model? Creating a historical runs of that, because we have these models that run today, lots of them, right? But what if we had that model in 1992 or 2002? How would it have done those events? Not only does that allow us to assess skill, but it also builds confidence for the forecasters that are using these. We're going to provide outlooks going out through weeks 3 and 4. So for the Climate Prediction Center, that means out through days 15 through 28 days into the future. We're also going to look at potentially giving seasonal data and monthly data as well, and see if the total month forecast is any better than using a week 1 forecast, a week 2, and a week 3, 4 forecast. If you stitch together the constituent parts, do you get a better forecast if you just simply use a total month forecast? But obviously for different, that might be for water supply, not for short-term concerns. Next slide. There's a bunch of different methods on here we're going to work with. Physical Science Laboratory has a couple of neural network methods to provide our RFC forecasts, or hydrological forcings. We're going to potentially devise methods of subsample climatology so that they're consistent with the CPC outlooks. We're also going to look at where we can do any kind of downscaling. Should we do it on a hydrologic units, or should we do it on a database, on the spacing of the model grid? We're potentially looking at snowfall outlooks, seasonal snowfall outlooks, week 2 snowfall outlooks, and I want to hear also about what else we're missing we might need to look at. Next slide. And then we're also looking at doing water year outlooks, so forecasts that start on 1st of October and go to 1st of April. And then on 1st of November, it would also go through the 1st of April or maybe the 1st of May. We're still working out some of these details. But essentially CPC right now, we do 3-month outlooks. We're potentially looking at doing 6-month, 5-month, 4-month, kind of a cascade of outlooks. Next slide. I think that's all I had. I think I got close to 15 minutes.
Pretty close. Thanks, Matt. So next we're going to be hearing from Mackenzie Skiles. So Dr. Mackenzie Skiles is an assistant professor in the geography department at the University of Utah and director of the Snow Hydrology group within the Snow and Ice Laboratory. Her research aims to contribute to our understanding of seasonal mountain snowpack using remote sensing, physically based numerical modeling, and field observations. Her group's research objectives include improvements to near real-time monitoring and forecasting of snowmelt and constraining how this critical resource is changing over time. Her undergraduate degrees in geography and environmental studies are from the University of Utah, and she has a PhD in geography from UCLA. Dr. Skiles' presentation, titled Incorporating Remote Sensing and Snow Energy Balance Modeling into Runoff Forecasting in Snow-Dominated Watersheds in the Colorado River Basin, connects to the need for improved snowpack observations and testing the use of these in a modeling framework, which is one of the opportunities laid out in the State of the Science report. So now I'll hand it over to Mackenzie for her presentation.
Thank you, and thanks for having me. I just wanted to recognize that the funding from this work is coming from NASA Earth Science, Applied Sciences, and then that I am working with the USDA ARS Northwest Watershed Research Center on this project. And the primary stakeholder that we're working with is the Colorado Basin River Forecast Center. And then finally, I just wanted to recognize my PhD student, Joe, who is doing a lot of the work that I'm presenting today. Next slide. So, I might be preaching to the choir here, but the Colorado River primarily originates as snowmelt in the upper basin. And the snowmelt rates and resulting hydrographs are controlled by net solar and long wave radiation, which are really dependent on the snow covered area, snow albedo, and atmospheric conditions. But the CBRFC operationally uses a temperature index model, Snow 17, that can't explicitly address these controls on snowmelt. The melt index and model effectiveness is diminished when conditions are outside of the calibration period. So the sort of example I like to use for this is, modeling capabilities have advanced rapidly, and the CBRFC and Snow 17 is kind of like using a landline in the modern era of smartphones. It's really outdated, and we know that as climate change advances, that more and more so, we're going to be outside of calibration conditions. So relying on index-based methods really should be retired. And we should be doing physically based modeling, especially for snow. Next slide. So in addition to just general energy balance, the Colorado River Basin headwaters have kind of a specific problem that other snow-dominated watersheds might not have, and that's dust on snow. And recent work has established that episodic dust deposition is really critical in this watershed. So dust radiative forcing advances melt, shifts timing and intensity of peak runoff, and controls the steepness of the rising limb of the hydrograph. And we've been able to correlate forecast errors from snow 17 to dust radiative forcing. And that just points to the fact that we really need to update these methods. So the CBRC recognizes that dust on snow is important in their watershed. And they have worked to incorporate remote sensing retrievals of dust impacts, but they're doing this by manually modifying the air temperature forcings to the snowmelt volume. So this is really time intensive and dependent on forecaster knowledge of both the watershed and the dust impacts. And we really should be providing a method that doesn't require in-depth forecaster knowledge to adjust those forcings. Next slide. So the project objectives for our project is to fill the gaps between sparse in situ observation networks to produce realistic maps of snow-covered area, snow water equivalent, and stream flow from snowpack outflow. And then we also really want to build the capacity of our stakeholder to run a physically based snow energy balance model that assimilates NASA Earth observations. And then provide access to data, products, and tools and training. So everything we're developing is open source. Next slide. Okay, so we selected the snow energy balance model that is known as iSnowBal, and it's the core of the automated water supply model, which has been extensively tested over large watersheds. So this is really a workhorse model. It's used by multiple groups to represent snow energy balance and snowpack outflow. And this physically based, spatially distributed model is driven by topographically corrected estimates of shortwave and longwave radiation, temperature, humidity, wind, and precipitation. So these forcings can come from point stations and then be distributed using a DEM, or they can come from weather models. So something like HER or Warf can also be used to force the model. But we all are aware that we lack local and relevant energy balance observations. We have very few stations that actually measure energy balance forcings. A lot of SNOTEL stations don't measure the net radiation fluxes that we need to force this model. So we really need to look to other sources in order to get the data we need, because your model is only as good as your inputs. So if we go to the next slide. The way that we are approaching addressing this is that we are going to assimilate remote sensing imagery from both MODIS and GOES to inform net radiation. And specifically what we're doing with MODIS is we're using snow covered area and snow albedo to update the net shortwave. And then we are also using cloud cover from GOES to update both shortwave and longwave. And then our forcings for iSnowBal are coming from HER to inform the meteorological variables. So ultimately, you know, we can't just stuff in the remote sensing and HER variables. We actually have to develop a framework to collect and store the new data streams, produce and quality control the model variables. And then we also have to figure out how to take these large data sets and make them operational. So how do we run the model as a part of a daily workflow? So we're getting to that point, but ultimately right now the step that we're at is actually validating. We're running the model over test watersheds and we're validating. We're validating with both in situ snow observations. So we're using whatever energy balance sites that we do have. And then also spatially distributed snow depth and albedo from NASA's Airborne Snow Observatory. If you go to the next slide, this should just pop up. Yeah, so I'm sure some people on this call are aware of the ASO project, but in a few watersheds across the Western US and a few watersheds in the Colorado River Basin, we have very high resolution snow depths from ASO, which are LiDAR based. And that's really a really valuable way to validate our spatially distributed model. Next. So this is what the framework looks like right now. We use the HER model as our forcings, and then we've sort of focused initially on MODIS snow albedo to update net shortwave radiation. And it all goes into sort of this database, and we're focusing on the Upper Gunnison right now as our test watershed in Colorado. But within the automated water supply model, we first do a wind simulation, then we distribute all these forcings that goes into the snow model, and what we get out is evolution in snow cover at an hourly time step over an entire water year, and now multiple water years. Next slide. So we first ran the model in a relatively small basin in the San Juans, Senator Beck Basin. And we did this because this is one of the few basins in the Western US that has 2 snow energy balance towers within watershed boundaries, as well as a stream gauge at the pour point of the watershed. So it's really one of the best constrained watersheds in terms of snow energy balance. And it also has multiple ASO overflights. And so what we did here is we ran the model, just baseline model runs. So that's standard, no updates to the model at all. And then we tested updating albedo in multiple ways, including from remote sensing and a direct update from an ASO flight. You want to go to the next slide. This might show it a little more clearly. What we did is we were able to compare no albedo updates in the state of the model to albedo updates. And what we found is that without albedo updates, the snow model missed snow melt timing by 2 weeks. So it kept snow cover around for too long. And when we update albedo, which is the primary control on snow melt in most snow covered environments, then we were able to match observations and match snow melt timing. And this was a very valuable sort of first test case for us to validate our hypothesis that albedo is the main control on snow melt timing. And it's worthwhile mentioning that there's a big push to incorporate the National Water Model into forecasts, and the National Water Model is using NOAA-MP as their snow model and snow representation. And over again, the NOAA-MP is getting snow melt timing incorrectly, and that's because they're not, or my hypothesis is that's because they're not updating the snow albedo. So without an accurate snow albedo, we can't really get snow melt timing or snow melt magnitude constrained. Next slide. Okay, so this is really the most exciting outcome of this project so far is we've been able to run iSnowBal over the Upper Gunnison for 2 water years now, water year 2018 and water year 2019. I'm showing a subset here, the East River watershed, which is a representative headwater catchment of the Colorado River Basin. The average elevation is just over 3,000 meters, and there's some decent topographic relief within this watershed. And it's got kind of everything there. It's got pronounced gradients and hydrology, geomorphology, geology, vegetation, and climate. It's also not as heavily dust impacted as the San Juan, so we get something that's a little more representative of the full headwaters. So this watershed we also selected for a couple other reasons. It contains the Rocky Mountain Biological Laboratory and is also a DOE watershed scientific focus area. There's a lot of data available within this watershed that we can use to assess our model runs. Additionally, the Airborne Snow Observatory has flown over the Upper Gunnison multiple times over multiple seasons. So we have that as a validation data set. And then the East River Watershed represents the area above 1 CBRFC forecast point. That's east above Almont. And that really allows for ease of comparison. So when we have snowpack outflow from the model, we can directly compare that to outflow at the stream gauge, along with their forcing variables in terms of precipitation and temperature that they use for snow 17. We can compare our forcing variables that we're using for iSnowball to see how self-consistent the forcing variables are between what we're using in our model and what they're using operationally, and see if there's a mismatch in those. Because when we hand over iSnowball to CBRFC, we want them to be able to use data sets that they are already familiar with and using in-house. And if that means using a temperature data set that they've already been using, then that's great. And normally this would be a video. I would show you the evolution of snow cover over the East River Watershed, but we couldn't have videos in these presentations. So if you're interested in seeing the model runs as videos, feel free to send me an email, and I'm happy to share those or discuss more about our efforts in the Upper Gunnison. After we go through and fully validate these, then we will move on to other watersheds within the headwaters. Next slide. So I wanted to point out this was open source. Everything we're doing is open source, and the automated water supply model is open source. Everything is available on GitHub. And we've created this flexible installation of the automated water supply model on a local environment. So you can install it just like we have and are running it. So you can go to my group's GitHub page to find that. And again, I just wanted to recognize NASA Earth Science Applied Sciences for funding this work. We're about halfway through a 3-year project, and we're getting really exciting results so far. And with that, I will end.
Thanks, Mackenzie. So next we're going to hear from Andy Wood. Dr. Andy Wood is a project scientist with the National Center for Atmospheric Research's Applications Laboratory in the Climate and Global Dynamics Division in Boulder, Colorado, and is also an adjunct professor at the University of Colorado. He has over 20 years of experience in academic, private, and public institutions. His current work centers on practical applications of scientific advancements in hydrologic, weather, and climate modeling, and predictions and projections to improve our understanding and management of water, energy, and terrestrial systems. Dr. Wood's presentation, titled A New Hydrometeorological Modeling Resource for U.S. Water Resources Applications, addresses the state of the science opportunity for a new approach to hydrologic modeling that can provide an alternative to or supplement current operational forecast approaches. So now I'll hand it over to Andy.
Thanks, Sarah. As you said, I'm going to talk about a hydrologic modeling resource and also a couple of sort of meteorological modeling resource that we've developed over the last 5 years or so at NCAR, and I list some of my collaborators there. Next slide. One of the things our work is sort of notable for over the last, this body of work, is it's been funded by federal agencies that not only include sort of the science agencies we typically think of like NOAA and NASA, but also water agencies, Corps of Engineers, Bureau of Reclamation, along with a little bit of funding from NCAR and NSF. But working with a colleague, Martin Clark, early on, we kind of laid out an idea of a sort of a strategic plan for what we wanted to do over the next 5 to 10 years, and thought about areas where we really needed to bolster current capabilities. And, you know, broadly speaking, they break down into better meteorological analyses, kind of in real time and over the long term, not only for the US, but for other parts of the US we don't, that are outside of CONUS. like Alaska and then some other territories, as well as better downscaling methods and better hydrology and land models, which include not only hydrology, but also the routing. And this is in support of climate applications and forecasting type applications as well. Next slide. So if we think about the major hydrology models that have been used, particularly in the Colorado Basin over the last really 20 to 30 years, one of the workhorses is of course, the Snow 17 Sacramento kind of sequence, along with other models built into the National Weather Service river forecasting. This is a sort of conceptual, low-dimensional approach, breaking up the watershed into a small number of storages at a fairly lumped scale. Next slide. And this just illustrates this is taken from the time I worked at CBRC, some of the sort of zonal breakdown that you see around Salt Lake City in the Wasatch Range, and this lumped approach to modeling, and then over the entire basin. Next slide. Another model that's been used really extensively in the basin is the Vic Hydrology model, variable infiltration capacity model developed at University of Washington and Princeton. It's been used really extensively in part for climate change, and this is examples from a study I did with downscaling climate model data for impact analysis in the Colorado Basin back in the early 2000s. I also ran it within forecast systems across the West for 5 years while working at University of Washington, and doing things like ingesting CPC and climate model forecast and assimilating SNOWTEL and MODIS-based snow information to see if that could benefit seasonal water supply forecasts. But if you go to the next slide, that's certainly one representation of the hydrology. If you think about what the model grid cell implementation, which has typically been for Vic on an 8th degree and more recently on 16th degree, it's one which lumps in a lot of different types of hydroclimates and processes into this gridded framework, which is quite different from the approach taken by the more watershed aligned modeling of the river forecast centers. Next slide. And then more recently, we have, of course, the Warf Hydro sort of very high resolution, very process oriented modeling that's been implemented for ostensibly street level prediction with 1 kilometer resolution models. As Mackenzie mentioned, the NOMP is the land model, coupled to even finer resolution, like 250 meter resolution terrain routing models and routing. And this approach is actually quite computationally intensive for use in seasonal prediction applications. And so the sort of growth of modeling in this water supply arena has motivated, if you go to the next slide, this work that we're doing now, which is to see whether we can bridge the gap between this sort of move toward very high resolution, heavy, computationally intensive, complex process models, and the more traditional, lighter watershed conceptual models that have been used in operations and operational applications for many decades. There must, in my thinking, there must be a middle ground where we can achieve some of the process improvements without going so heavy that we can't use the models in the way we need to with hindcasting and long-term simulations and ensembles particularly. Next slide. So for this, we turn toward an approach that kind of sits in the middle in the sense of resolution. This medium resolution, ensemble, uncoupled, over the loop approach. And by over the loop, I mean an approach that you can run kind of on a supercomputer without manual intervention versus the more in the loop approach in which these lower dimensional models are run kind of on smaller workstations with manual intervention by the forecasters. if we really want to step up our complexity and be able to bring in different kinds of alternatives and run longer ensembles and over wider domains and with more frequent updates, we do need to, I think, move toward more of an over-the-loop approach that is more reproducible and supportive of techniques like data assimilation, as the earlier speaker was referring to. So in any case, we adopt this medium resolution ensemble couple approach. We're using a model called Zuma for the most part, although I also have another project in which we're trying to do the same thing with Warf Hydro to support maybe a more agile long-range configuration. And I'll talk about Zuma a little bit in the next few slides. Next slide. Zuma is really more of a framework than a single model, although once you've made some model choices as to the parameterizations that gets used in the model, it becomes a model that you can use like any other model. But the idea behind Zuma, which is Martin Clark's creation at NCAR, Martin Clark is now at University of Saskatchewan, is to build a platform on which you can really explore different hypotheses about how to model a watershed. You know, how we may agree for the most part on what the various components of the water balance are and the energy balance and how they're linked and what the various processes are that affect those components. We don't necessarily agree on how they are specified and how, you know, the best way to actually describe something like the vertical redistribution of water in the soil. So this model, which is a big chunk of Fortran that we can compile and run on supercomputers, is a way to get at those and test some of those hypotheses. Next slide. It also lets you explore different ways you may want to discretize or break up the model, not only in space, but also sort of the subsurface arrangement of soil layers and aquifer. Do you want to run it in a gridded fashion? Do you want to have a hierarchical, you know, watershed hydrologic response unit approach? Do you want to run it on a watershed aligned basis, which is what I've done in this work? Next slide. And so over the last couple of years, I've been working hard, and this is in part with support from NASA, to build out an a priori configuration of this model for the whole country that we can kind of use as a starting point. So you need things like parameters. You have to make a choice about resolution, about soil layers, snow layers, the time step of your forcings. And so we've basically built out this starting point with this modeling system that fits over this NLDAS region shown here. Next slide. And we've broken out a whole range of parameters that relate to different particular processes that we know that we will need to calibrate. And so we've exposed these so that we can use them in our calibration routines. And this is just sort of a quick list to show how those are distributed. Next slide. And on top of that, we've also implemented a new channel routing model, which was built by Naoki Mizukami and Martin Clark, called MizuRoute. It has multiple methods, you know, diffusive methods, kinematic methods, and it is capable of running on everything from the finer down to the finest scale routing networks we have available right now, which are the NHD Plus as extended to OCONUS, which is the 2.7 million stream segment routing network that's used in the National Water Model. That is ultimately too much of a bottleneck to run for water type applications like long range water supply. So we use another 250,000 segment scheme that covers the whole US as well. And this just kind of illustrates what that looks like over the upper Colorado Basin. And there are a lot of other features within this, including some really nice work to make it parallelizable and fast, which is needed. Next slide. And then another component that was in one of my earlier slides was the meteorological analysis part. And so for that, we've also developed a new strategy for creating surface forcings for models. And the technique was first outlined by Martin Clark and Drew Slater as applied to snow data sets in 2006, and then reapplied by Andy Newman and others at NCAR for meteorology in 2015. It's basically a spatial regression that's forced by terrain, and more recently we've included her as a predictor to develop sort of fields of precipitation and temperature and other variables over space that reflect the influence of terrain in explaining the kind of observations that you get at any particular time. And because it's a regression, it provides uncertainty, next slide, from which we can extract ensemble members or ensembles and make, instead of just your typical interpolated data set where you just have gridded fields with no real estimate of uncertainty, we now have gridded fields that include, in the form of ensembles, that include an understanding of how certain or uncertain we are about the data at any particular location. Next slide. I'm sorry, I'm going through this a little fast, but there are a lot of components to the work. Just to illustrate this Newman et al. Data set, which is this one in the middle in the bottom row, it actually turns out to be a really nice data set in terms of its characteristics for things like trend estimation, and it's the fact that it's long-term. I have a version that starts in 1970 and goes all the way till yesterday. It's a real-time data set, both daily 8th degree and 16th degree. It makes it very suitable for forecasting. And we don't, I think because of the spatial terrain approach, we don't run into some of this sort of, pockmarked type features that you see in the data resulting from interpolation methods that are used in other common data sets like Livnet et al. And Daymet and then LDAS and so on. It's more like PRISM in that sense. Next slide. So the nice thing about this data set is having the uncertainty in the meteorology is that we can then use it to create uncertainty in the hydrology. There's a lot, when we do an estimate of a watershed, of a small area, the forcings up in a watershed, we really don't know those with a high degree of certainty. And so being able to represent what we do know and where we have less confidence in our forcings is really important. So this is a comparison of showing an ensemble run of a hydrology model with the ensemble members in gray versus the observations, and seeing that, in comparison to just having one single member, we can see where we might think our model is kind of reasonably encompassing the observations, where otherwise we might just think it disagrees. Next slide. So back to the modeling. So we have this high quality ensemble forcings at a variety of resolutions. And then back to the modeling, we've gone and taken that a priori gridded model and turned it into more of a watershed model. And this is my projects that I have now are focused on HUC-12 based modeling delineation. And so this kind of shows what that looks like over the upper Colorado with the different polygons. And this has been implemented over the entire West, going all the way to about the Mississippi. Next slide. This shows a little bit more of a drilled in look at what that resolution of a model looks like. HUC-12s are, I think, on average about 90 square kilometers. And our first approach with this is lumped. This is showing how a model looks going into the Buffalo Bill Reservoir in Wyoming, where there are two forks on the right leading into the reservoir, and they're each broken down into 16 to 18 sub-watersheds. And this shows the merit based stream network that comes out of those watersheds. And again, thinking back on what we want to do with this kind of modeling, it's not necessarily to do flash flood type prediction on every small creek, but it really is to do things like river flood prediction out 10, 15 days, and water supply prediction out 9 months to 2 years, and even climate change projection. So that's the reason for selecting this slightly coarser scale as a starting point. Next slide.
You have 1 minute left, Andy.
I do? Okay, let me whip through. I just want to illustrate that we've now implemented this model for water supply prediction, and this is showing an example again in the Buffalo Bill. We've also done this in the Upper Rio Grande. And can you skip several more slides? Next slide. And yeah, that's the one. And this shows that we've also implemented it into a real-time prediction system, which is updating it every day and simulating the entire West. And this is just showing an out-of-the-box prediction and the Tuolumne. For this, we haven't even calibrated the model there. There's certainly a lot of places where the model's not working as well, but it shows that in general, we started with a pretty high quality set of components from the meteorology to the model. And now that it's all come together and we're starting to use it for water supply prediction and a number of reclamation applications, we're pretty excited about where we can go with it as one of the newest kind of modeling entries into the Western US. And so I think I'll stop there on that slide. And whole point of this is really just to introduce this as an option to people who are doing these kind of studies in the future. Thanks.
Thanks, Andy. So our next speaker is Sean Fleming. Dr. Sean Fleming is an applied R&D technical lead with the NRCS National Water and Climate Center and an affiliate faculty at Oregon State University and the University of British Columbia. His degrees are in geophysics, geology, and civil engineering. He has 25 years of experience with environmental modeling, monitoring, analysis, and prediction, and has worked in research, operations, and management. He's also strongly active in science outreach, giving talks at the Smithsonian and at Science Pub events, and writing for Princeton University Press, Scientific America, and Wired. Dr. Fleming's presentation, titled An Introduction to the New NRCS Water Supply Forecast Platform for the West US, a metasystem blending AI, geophysical knowledge, multimodal inference, and practical requirements, connects to the state of the science opportunity for a new approach to hydrologic modeling that could provide an alternative to or supplement current operational forecasting approaches. So now I'll hand it over to Sean.
Great, thank you very much. So yeah, let's just skip forward to the next slide. So yeah, just like to thank my authors and various other co-authors and various other folks who've helped us out over the years with some specific technical guidance. So yeah, let's just skip forward to the next slide, please. And the one after that. Great, thank you very much. So yeah, water management, water resource management has always been crucial to human civilization, and things are no different today. Even modern high-tech manufacturing tends to be quite water intensive. Growing populations in the US West, for example, as well, and climate change, which may be reducing manageable supplies and certainly increasing the uncertainty. The ability to predict what's coming up next so that we can plan for it and manage it is becoming increasingly important. It's as important as it ever was. So next slide. One of the sort of the information backbone for if you will, for doing that in Western North America as a whole are operational water supply forecasts. So I suspect most people on the call know exactly what this is, but just to be on the safe side, these are forecasts that are typically issued once per month or so, more often than that, depending on the agency and the location. That process usually starts in winter, and the predictions are made of spring-summer total flow volume for a given point on a given river. And by operational, we mean that it's being performed by institutions having direct accountabilities to end users around generating these forecast products and doing it accurately. And the primary basis for doing that in the Western US certainly is snowpack information, but there are a bunch of other things as well. So let's skip forward to the next slide. So water supply forecasting at the U.S. Department of Agriculture, Natural Resources Conservation Service, or NRCS. I'll just summarize that briefly. So we operate the largest standalone operational WSF system in the U.S. West. If you took the NWS RFCs covering St. Mary and Adel all together, they would be larger. And it may be the largest statistical operational WSF system in the world. So if anyone has any more information on that, I'd love to hear it. But as far as I know, that's true. And it's definitely a huge system. There's over 600 forecast locations, each with multiple issue dates and target periods. We actually have several different forecast technologies in use, but the core method and what tends to be associated with NRCS the most, because NRCS introduced this, specifically David Guerin back in the early 90s, has been adopted elsewhere as well, is principal component regression. So let's just talk about that very quickly. Next slide. So PCR, it's basically two separate steps, more or less separate steps. The first is a principal component analysis is applied to the input variables, and then the results from that are used as candidate predictors in a forward stepwise multiple linear regression. And the advantage of this over conventional regression is that it addresses multi-collinearity issues and reduces the dimensionality of the input variables. And that's quite important for typical WSF applications. And then, of course, NRCS implementation follows a specific path around feature selection, developing confidence intervals around the best estimate. It is a probabilistic forecast technology. But yeah, I'll let it go at that. Let's go to the next slide. So that's kind of where it's at. Now, where are we going? So the system has been in place at NRCS and other places for quite a long time. So we're looking at building a next generation system. And to do that, there are a number of steps that had to be undertaken. I'll just briefly mention these. One is to clearly document the existing system. You know, forecasting systems, operations tend to be kind of organic and evolve over time. So we wanted to make sure that everything was documented well. There's quite a bit of testing and also documentation of NRCS experience around the abilities and limitations of the current system, you know, what you'd like to see in a new system. A review of data-driven WSF modeling progress, took a quick look at the implications of anthropogenic climate change, and then did some initial experimentation, some blueprinting, and some preliminary scoping models. Next slide, please. And we landed on the use of machine learning. So I'm not going to go through this whole table here. One punchline, you know, especially in operational hydrology applications, but it's true generally, of course, is that which class of models is quote unquote best. It depends on what you're aiming to do. So the main punchline specifically around machine learning is relevant to WSF at NRCS is that it gives overwhelmingly good bang for the buck as a predictive tool. It's, you know, leveraging the data science all around us to produce better, cheaper WSFs. But one lesson learned from previous applications of machine learning, both in this area and in others, is that you can't just throw it at a problem and expect it to work right. You really have to approach it in a very application-specific way. So next slide, please. So machine learning has had kind of a long and somewhat mixed history in hydrologic prediction. I built my first neural network, including a screening algorithm from scratch without using any libraries or anything in Fortran on a SunSpark workstation back in about, I don't know, 2002, 2003. So in the intervening, you know, a couple decades almost now, I've been, you know, continuing to work on and off on this area, and it's really been interesting to see how things have evolved or not evolved. And you know, the first papers using AI for river forecasting date back all the way to '95, and there's been some challenges kind of mainstreaming that into operational hydrology and operational WSF specifically. Some of those are just kind of unfortunate, people aren't familiar with it or they don't understand it. Others are more questions of design issues that just have not been addressed over the years. But things are definitely changing. And I really know this is really picking up speed maybe about 5 years ago. Everyone's just getting used to the idea of AI, even if they're kind of bah humbug about it. It's just in your everyday lives. The tools are also far more accessible, and there's a much more diverse set of methods, which actually really helps a lot with hydrologic applications, which have some pretty specific requirements. And things like explainability, overtraining, prediction uncertainty, all these things can now be really addressed head on. Next slide, please. So basically the key in a nutshell is to kind of is summarized by this little Venn diagram here. So you've got this whole body of machine learning knowledge. It's very large, it's very diverse, and much of it is not relevant, but parts of it are. And you got to intersect that with hydrologic science. It's got to produce results that are consistent with and interpretable in terms of the physical hydrologic science. And then that also has to dovetail with very specific pragmatic requirements of a genuine operational forecasting environment. Next slide. So out of that entire process, we came up with some key design criteria: improving forecast uncertainty, improved potential for automation, low cost, ease of development, addressing some known technical issues around nonlinear forms and complex residuals that complicate the calculation of prediction uncertainty, modularity and expandability, geophysical interpretability is important, a whole bunch of, just a laundry list of different things here. So whatever we came up with had to satisfy all of these requirements. Next slide, please. And what we came up with, we've dubbed M4, the multi-method machine learning meta system. That's kind of the prediction analytics engine under our next generation system. So next slide. And I'm not going to have an opportunity to summarize in detail here. This flowchart kind of summarizes some of the key elements. So there's a number of carefully selected modeling threads. And these were chosen to handle heteroscedastic non-Gaussian residuals and nonlinearity, and to allow physicality constraints like monotonicity and non-negativity, which we know a priority need to be applied. And then all of that then is in turn combined with dimensionality reduction, a genetic algorithm for optimal feature creation and selection, some parallelization, a bunch of other stuff. So what we get out of it in the end is a integrated modular and multi-model ensemble kind of system of systems is the way that we're looking at it. Next slide, please. So I'm going to focus on two parts of it. One is achieving AI intersections with process physics. So there's a number of ways that we've done that. One is through maintaining the current practice of kind of hands-on features engineering, because this is where a hydrologist has an opportunity to say, I know what the key drivers are, and I'm going to throw them in there into my input data. Reframing the entire thing as a low-dimensional problem with a parsimonious solution. So there's specific technical steps that are undertaken to achieve that. And the result of that is that you wind up with something that's straightforward enough that you can actually graphically visualize input-output relationships, which is really important for having this physical explainability. And also the application of monotonicity and non-negativity constraints is also really important. Yeah, so that's kind of the explainability angle. Next slide, please. In a nutshell, anyways. The other part is autonomous machine learning, or auto ML. So you needed something that an operational hydrology team whose expertise is not necessarily in AI can take this and use it really efficiently and really effectively. So what we wound out with was a lot of preliminary testing, sort of converging on reasonable default choices for a lot of the hyperparameters in the various machine learning applications, including things around regularization in particular. And where one selection wasn't deemed sufficient, there's algorithmic logic built into the system to pick the right value for that particular problem. Next slide, please. So I'll give you a quick application example. This is from the Owyhee River. which is kind of in the very northwestern part of the Northwest, or of the Southwest rather. And it's known from experience to be a particularly troublesome forecast point. Next slide. So this is an example of what a more conventional principal components regression WSF model gives without going into it and having to like yourself manually make a lot of choices to alter things. You've got negative value predictions, you've got prediction intervals that clearly don't work. There's just a lot of things going on here that are just less than ideal. So next slide. This is what M4 does. So it gives results that are physically reasonable, including non-negative, right across the entire prediction intervals. Prediction bounds vary in width from year to year. They're allowed to be asymmetric, which is also a requirement. The whole thing's relatively robust to outliers. And the whole thing's actually pretty much automated. This is a totally hands-off process, kind of a turnkey system that just produced this without having to go through an in-the-loop process, to use the term that Andy just did. This is pretty much an over-the-loop system. Next slide, please. So that was just one example. We've done some fairly exhaustive testing. One is a set of hindcast tests spanning 20 test cases over 11 locations across the western US and Alaska. Basically, it beat the old system, and the old system is actually a pretty good benchmark, reflecting how also, for example, NWS, RFC, ESPs work, and various other technologies. So it beats existing systems. And there's also some interesting things we won't have time to get into here about how using 6 different machine learning methods within this system is really effective at dealing with equifinality and providing a much more robust and reliable model. Next slide. So in addition to that hindcast testing, we also did live operational testing at a selected subset of 5 forecast locations during the last forecast season. This confirmed the feasibility of workflows in, a kind of genuine operational setting where, there's time and data constraints. We were able to rebuild some of the models on the fly because COVID-19 created some data issues. And in particular, again, I don't have time to run into it now, but it turns out to be really easy to craft a straightforward storyline about the issued forecast in terms of current, snow conditions and things like that, just like you would with a PCR or process simulation model. Next slide. No, next. Yeah, perfect. Thank you. So just to wrap up, what are our current next steps? So we've got this prediction engine built. There's some refinement on that, as well as a platform to run it more conveniently in an operational setting and a team setting. Other R&D directions, we're looking at supplementing the current supervised learning method with other techniques that may be a little more interpretable, not necessarily more accurate, but more amenable to physical interpretation. Really interested in looking at using snow remote sensing or data assimilation data as inputs. The whole thing is built to be modular, so we can integrate other AIs into it. So that's something I'm definitely looking to do. Experimenting with new sources of seasonal climate prediction information. So, for example, seasonal climate, numerical climate models or climate indices. And just to wrap up, one thing we're kind of interested in doing going forward is to use this as a more generalized forecast integration platform. So the idea here is to expand the scope by not only having its own internal 6 models, which are all integrated, but also ingesting probabilistic forecasts from external sources, including process simulation models. So that includes some PRIMS models that are being built internally, potentially a national water model. Really, the main thing we'd be looking at there, I think, perhaps, would be the RFS or RFC rather, ESPs, which would create an opportunity for kind of a specific technical protocol for reestablishing interagency forecast coordination. So last slide. If you want any more info about this, the method has been published in the AI literature. So if you're really interested in the gory details behind this machine learning system, and you can find them there. And of course, feel free to reach out to us. And with that, I will wrap it up. Thank you for your time.
Thanks, Sean. So our final speaker today is Lindsay Barrett. Dr. Lindsay Barrett is a hydrologist with the Bureau of Reclamation's Technical Service Center in Denver, Colorado. She received her BS in Agricultural and Biological Engineering from Pennsylvania State University and an MS and PhD in Hydrology from Colorado School of Mines before supporting Lawrence Berkeley National Labs as a postdoctoral researcher in the East River Watershed of Colorado. At Reclamation, Lindsay supports long-term water supply, water quality, and reservoir operation studies with particular interests in snow and evapotranspiration processes. Dr. Barrett's presentation, titled Merging High-Resolution Airborne Snowpack Data with Existing Long-Term Hydrometeorological Observations to Improve Water Supply Forecasting, addresses the state of the science opportunity for improving the snowpack observations in this basin and testing the use in a model. So now I'll hand it over to Lindsay.
Thanks so much, Sarah. So this project I'm talking about today is a reclamation-funded research project through our Research and Development Office, but I'd really be remiss if I didn't mention my collaborators loudly up front. Ethan Gutman at NCAR has really taken the technical lead on this, supported by Andy Wood and Kostas Andriadis, who are doing a lot of the modeling you'll see that's coming along, and of course Tom Painter, as we are using ASO data, so listed there as well. So I like going last year. Well done on the slide transition, because I feel like the motivation has really already been laid out there. We've heard kind of over and over again how both observations and models are advancing. And one area of this advancement is really the ability to capture spatial variability. So I kind of went down a wormhole of NRCS historical photos, but I bring you a couple here today. You know, we've come from the 1950s where we have snow course measurements and sort of an iconic picture there to what's becoming an iconic picture on the right of the ASO plane flying over the Tuolumne. And I think, as Mackenzie nicely introed, the Airborne Snow Observatory is providing these spatially comprehensive data sets of snow depth, and eventually snow water equivalent that really provide interesting opportunities. So just as these observations are advancing, so are the models we can adjust them into. And so that was really the goal of this approach. That long title could really be shortened into how do we use ASO to improve our water supply forecasting. And so we take what's listed here as a 5-step approach to answering that question. But we're starting with the statistics of the ASO data. And this is allowing us to look both at the spatial distributions and compare that back to what's historically been used, some of the snow pillows and index stations in the area, and also to generate a historical ASO-like data set from 1980 to 2013. And that kind of hits all the way back at what Matt mentioned of kind of having this history to compare our forecasting models back to. And we will also use those statistics to create statistical forecasts. And this allows us to compare the trade-offs in the long-term record of the index stations to spatially resolved data of ASO. Oh, I'm sorry. Yes, this slide. With the ASO-like data as an intermediate that may be able to shine some light on how to best assimilate the data into our forecasting efforts. And so that's that third bullet you're seeing anyway there. And that's building these more physically based modeling approaches and implementing them for forecasting. And that's sort of where we're at in this process so far. And then these models will ultimately be used for an ensemble streamflow prediction forecast and looking at how to best assimilate the data, both the ASO data and the extended index record ASO-like data into these forecasting methods. And there's one little additional piece here, and that's the quantification of the number of ASO flights required. Required perhaps should be in quotes. I think we've kind of heard this message too, that required is all based on what you're looking for. So how many required is obviously based on your goal and what you're looking at. So all of this work is done in the Tuolumne River, which is what you see there on the right-hand side, the basin there. And this is really done because the rich history of ASO flights there. There are some ongoing efforts in the Colorado Basin as well that are also looking at how to get this type of information into the CBRC's forecasting system and the improvements that are possible there. So we're kind of working together as this impacts all snow-dominated areas. But so for those of you that don't know, the Tuolumne is located in the Sierras within Yosemite National Park. It supplies water to the Hetch Hetchy Reservoir, which is the water supply for San Francisco and others. So not only is it an important watershed, but it has a rich data history. Next slide. So that first step is the statistical analysis. It is nothing like the machine learning you just heard about. Here we're using a pretty simple multiple linear regression between the snow pillow index stations to predict the basin average ASO SWE. And this is what allows us to generate that ASO-like data, that historical data set as well. And there are 15 snow pillows we're looking at, so not all of them are located within the basin, but some of them provide some of the kind of missing high elevation data that might be particularly important. 53 ASO flights, and we're using different versions of multiple linear regressions here. You'll see this in the next slide, to try and remove some of the overfitting. Of course, there's always the assumptions built into linear regression here, and some collinearities and things that we're attempting to reduce the impact of, but haven't gone fully to more of a PCA type approach. And there's also many possible combinations of stations and flights. We've looked at quite a few of them, and we typically found that 2 to 3 stations were selected regardless of the year left out in the leave one out validation approach. So we move forward with 2 to 3 stations, but there are many possible combinations of flights and stations that could be used, and other statistical methods to explore as well. So if you go to the next slide, you'll see an example of this MLR approach I was just talking about. On the left-hand side is the regression with all 15 snow pillows in there, and we use that to the predicted basin SWE. We're regressing here against the ASO basin SWE. And so you can see, as you would expect, perhaps a very tight relationship between those. There's obviously some overfitting happening here. But we get a root mean square error of about 12 millimeters in this left-hand side, this left plot. And what's mostly nice to see about this plot is that we have a pretty sensible relationship here. And historically in these lumped kind of large spatial scale hydro models, this was perhaps an appropriate tool. But what you see as we start to kind of break that relationship up a little more and make it a little more robust in the right-hand plot, is that relationship becomes less tight. And so this is cross-validated using a leave 1 year out approach. Basically, each year of data was left out, and a stepwise regression was performed on the remaining stations to find, quote unquote, the best stations. And then this regression was fit to predict the flights that were left out. And so a slightly more robust approach here. And now we're looking at root mean square errors on the order of 27 millimeters. So while the variability is obviously still explained, 27 millimeters is substantial over a basin, and something to think about from a forecasting perspective. Next slide. And of course, not all errors are created equal, if you will. You'll notice in these plots, there were also going to be a video, Mackenzie, but I've pulled a few out that make the point here. This is the simplest linear model from that previous slide, and you can see how the error relative to the ASO data are typically larger at these high elevation areas where there is more snow but fewer stations, or potentially more snow but fewer stations. But it's not always in the same direction. And as you think of this 12 millimeters or 27 millimeters of error over this whole basin, you're starting to equate to a lot of water. And so this all sort of supports this idea that if we move toward a less lumped model, we can capture the spatial variability in hopes of adding value to our forecasts and the information in them. But how to really do that is the focus of this study, because it's not always as simple as a direct insertion. And one more statistical piece before we kind of talk about where we're going with the forecast modeling is this sort of uncertainty across number of flights. A slide previously titled, how many flights do you need? But again, that depends on what your goal is. And so what you're looking at here is the change in the goodness of fit statistics, so just that R-squared value on the y-axis. Against what's on the x-axis is the number of flights used in the regression. So basically here, there are 500 randomly selected subsites from this full flight time series. And if we select 5 of them, the mean is that blue X associated with the 5 on the x-axis. The red is the best subset and the green is the worst subset. So what this tells you is, if you randomly select even 8 flights and you pick the worst ones, you're going to have no explanation of the variability in those flights. But if you happen to pick the best, you're up on the order of an R-squared of 0.94, so you're explaining about 94% of the variability. So some strategic flying is, of course, very valuable. But even with just sort of the average subset of those, you get these blue X's, and with around 5-6 flights, you approach that mean of that little ensemble coming in at about 90% of the variability explained. Which for some applications may be appropriate. And, you could use these types of relationships to get to your basin SWE from index stations. However, in some years it may not. And so as we start to kind of break down which years we're looking at, you can see in this particular slide that orange X's are the high SWE years. And so now we're kind of hitting that asymptote around 80%. Oh, I'm sorry, I didn't tell you to move the slide again. That would have been helpful. So you can see blue X's mean, orange mean of only the high SWE years, green low. So that was the worst subset, and red the highest subset. But basically, the main point of this slide is that as we start to look at sort of quote unquote atypical years, those relationships start to break down. And if you go to the next slide, you'll see that again. And so here the orange X's are, the previous one. The orange X's are the low SWE years. And so that's even worse than the high SWE years. We perhaps haven't even hit that asymptote yet. And it's taking 15 flights before we're explaining 80% of the variability. And so these plots are really just to kind of show you the trade-off between the number of flights and the information that we get. But what we're really trying to move toward, if you go to the next slide, is not just snow, but flow. And so that's moving towards flows into the Hetch-Hetchy there. So here you have 4 different scatter plots, and now we're looking at observed flow on the y-axis. And so that it's kind of a strange unit, I apologize for that, but that's cumulative CFS, cumulative cubic feet per second. But that range is about 0 to 240,000 acre feet with increments of approximately 40 that you're looking at there. That's an easier unit to think in. And so we have 4 different, what you could think of as predictors of that flow. The upper left is the flow simulated using the CNRFC's model, so the SAC-17 model. Moving to the right, you see ASO SWE. So that's just basin average SWE from the available ASO flights. And then the ones on the bottom are the reconstructed pillow SWE and the ASO SWE, both added with a fraction of the precipitation for the remaining year. So these flows are taken for these point measurements, 3, from the time of measurement cumulative to the end of the season, or basically July 1st in this case. So what you'll see in that upper left is the SAC model predictions. They're strong within a year. You see these nice linear trends, or at least trends, perhaps not fully linear, within a year, which you would expect is the cumulative nature of snow and these plots. But it kind of breaks down between years, and that's something we're working on is improving our SAC model that we're using here, because it's not exactly consistent with the CNRFCs. And then as you move to the right, you can see that ASO alone provides a more consistent trend across years, but in what could be low snow and resultingly low flow years, or could be low snow parts of the season during toward the end of the season, this relationship has a lot of scatter around it and could result in a lot of errors in flow for any given ASO SWE measurement. And of course, this is improved when you drop below that to the bottom right-hand corner by incorporating the precipitation that is remaining throughout the season. And then you start to get this really tight coupling between the ASO snow and the precipitation, tighter than to the left if you compare that to the in situ SWE. So those are the pillows. And this isn't altogether surprising because a lot of these stations that may be capturing the snow that is left during those times might be, particularly in the late season, the pillows may not be representative of what's there. And so you're seeing the value of those ASO flights during those types of year. But ultimately, these types of predictions provide a baseline from which to build the ensemble streamflow predictions that is kind of the goal and where the study's going. Because then we can start to account for the uncertainty in the precipitation over the rest of the season on top of a more ground truth snowpack. So if you go to the next slide, I'm actually going to breeze right through this one for the sake of time. But this is basically where we're starting with our CNRFC-like model, and so it's not actually like the CNRFC model yet. So I apologize for that, but what we're moving toward that so that we can match their template and for what their forecasts are actually like, and do some direct insertions of data. We've done some preliminary work there, and obviously it's not as easy as just putting the data in there. Sometimes it improves it and sometimes it doesn't. So if you move to the next slide, our next steps for that streamflow forecasting are updating the SAC SNO 17 model to be consistent with the NRFC implementation. So what you just saw on that last slide is sort of an offline model run outside of their forecasting system. But we've been working with them to kind of bring that in line with what the parameter sets and processes they're using. And then we can use that to generate some seasonal forecasts and do some analyses approach consistent, or at least to complement what the folks in the Colorado Basin are doing in the Upper Gunnison and other ASO flowing sites. But what we're really moving toward is working on best practices for assimilating this ASO data into model configurations using two other models, so Vic and Zuma. So Andy just gave a nice intro into Zuma. And what I'm showing here is an uncalibrated, sort of straight out of the box for his national model simulation in the Tuolumne, and it appears to have some skill. And so we haven't fully evaluated snow in that or calibrated it and looked and dug into the Tuolumne a little, but that's all part of next steps for this project. And that model is great because it allows us to look at different spatial representations and to see how, in what ways ASO can really benefit these types of hydrologic models. And so I think that's about it. I apologize for the slide lag and forgetting those reminders, but here's my email, one more historical photo for you, and a big shout out to Ethan, who's been doing a lot of the heavy lifting on this project.
Thanks, Lindsay. So now we're going to move into our question and answer session. So just a reminder, if you have any questions you'd like to ask our speakers today, put them in the box, the chat box. We already have some questions that have come in, so I'll start reading through those. To start with, I have a question for Mackenzie from Rebecca Smith. Are there other Colorado River Basin headwaters, high producing watersheds that would make good candidates for ice snowball? How much does the high level of data in current watersheds contribute to success versus a watershed that would have less instrumentation?
That's a great question. Let me make sure I understand it. So I think she's asking if there's other watersheds that we are going to run it over, or if there's other good candidate watersheds.
Yes, I think that's generally the question.
Yeah, and ultimately the goal is to run it over all snow dominated watersheds. But yeah, after we run it and assess it in the Gunnison, other target watersheds, we would like to move to the Uintas to kind of capture the other side of the headwaters. And then the Animus is another one that we would like to run it over. We are actually kind of letting the CBRFC guide where we would like to run it next so that we can compare to their outputs. And ultimately what they'll end up doing probably is, if this is successful, they'll be running iSnowbell side by side with Snow 17 as a supplement to their current forecast. So we're sort of relying on them to tell us where they would like us to run it next. But we did have to pick, like you mentioned, we did have to pick these heavily instrumented sites first so that we could assess the model, but we can move to other basins that are not heavily instrumented next.
Great, thanks. So I have a question for Matt. How could the subseasonal to seasonal precipitation and temperature experimental forecasts that extend out a few weeks be connected to the longer term ensemble streamflow forecasting methods that are used at the RFCs, which are dependent on that historical precipitation and temperature traces, especially if the subseasonal to seasonal forecasts are ensembles?
So the ensemble streamflow prediction right now, it starts off with observations, and then through day 10, it already takes in model forecast precipitation. And then after a certain period, it goes to climatology for that basin, for the years of climatology that they're looking at for its precipitation. It would simply be replacing the first 28 days of that, whatever inputs they have, with the forecast that come out from the Climate Prediction Center into that. And then after that, going back down to climatology. So it's very analogous to current methods.
Okay. Makes sense. Okay, so our next question is for Andy, also from Rebecca Smith. How would different sources of ensembles impact forecasts water managers use? Can you reflect on how the ranges of or features might differ from basing ensembles on historical observations?
Yeah, I tried to answer this briefly in the chat, which I probably shouldn't have done. But in any case, I think this GMET-based meteorology is pretty interesting to me for a few reasons. One of which is that in using it, I'm finding that it seems to be a little bit higher quality than some of the other interpolated forcings that we use. So right there, that's going to make a difference in how the use in something like an ESP type approach would play out. I know that, in the past, when forcings are developed for the RFCs, there's a lot of work to kind of quality control those forcings so that if they're, in part because you don't want errors in the forcings to show up in the ESP traces. The other thing is having the ensemble is really important for providing a way of estimating model errors, which are needed when you're doing a lot of ensemble data assimilation methods like ensemble Kalman filter or ensemble particle filter, which are going to be a strategy for integrating SWE and other types of basin observations. So it provides a platform that we don't really have right now. And then I think I said, something else, but I'm trying to figure out what it was. Oh yeah, we do find that if you use a model and ensemble meteorology and model calibration, it's helpful. You don't end up training to like a specific error that happens to be in your forcings to try to get your model to match that when really it's an error. And it's also been helpful, just the overall technique, infusing in other kinds of data sets. So far, we've looked at HRRR and blending in HRRR precip and temperature as we make the forcings, but in the future, we can also use satellite-based products or reanalyses or other types of gridded products.
Thanks, Andy. So we have a question for Sean too. And this is a multi-part question. So what is the reaction from operational forecasters Is there resistance to learning how to use it or skepticism? What would be the path for operational integration?
Yeah, thank you. That's a great question. It's actually been really smooth at NRCS, and there's a few reasons for that. One is the basic way the project was managed and the product was designed. Through the entire process, pretty much the entire forecast team at NRCS was involved, providing input and feedback and suggestions and critiques. So the end product reflects a lot of the things that the forecasters, the operational forecasters themselves wanted to see. And you know, the 9 design criteria that I listed in my slide and didn't quite have time to go over in detail, that's kind of a distillation of that at a high level, but there's also lots of specific, much more specific choices. So that helped a lot. The fact that the NRCS team, although they do have process simulation models in-house, that agency is focused, as are some others, on using data-driven methods as their core forecast technology and have for many years. So the idea of stepping to another data-driven system is a smaller jump for them. And also the way it was constructed, and in some ways it's radically new, but in other ways it's really just a hot-rodded PCR. And that helps a lot with people kind of understanding what it's doing, and it's kind of a general sense and how to use it and how to interpret it. So that's actually worked out really very well, just because of some choices we made along the way. As for paths for operational integration, that is a process that's currently underway. So one big step around that in practice, you know, in an operational setting, is that we need to build a software platform to handle the prediction engine that's already been constructed. So we can forecast using the prediction engine, but it's kind of clumsy, as any prototype is. So we need to build those interfaces with the user, with databases, with reporting tools, with mapping tools, all that kind of thing. That's part of a genuine operational system. So that's going to be going forward. We're working on that right now, and I imagine that when the time comes, we'll run the 2 systems side by side for a little bit and then gradually switch over. And the fact that within the new system, there's the ability to more or less replicate the old system also reduces institutional risks associated with adoption. There's kind of a backup plan within the new system if you want to look at it that way, which I don't anticipate ever really needing, but it's a bit of a security blanket, which helps with the buy-in as well.
Interesting, thanks. So there's another question from Mackenzie. Do you learn anything extra by having one dry year and one wet year? For instance, 2018 versus 2019?
Yes, that's a great question. And I think when we were picking the years that we wanted to run, we were limited by a couple things. One is the availability of PER data, and then also ASO data. And so we kind of looked at a set of years that we could run and assess, and then we picked 2018 and 2019, not only because they're the most recent years, and I installed a snow energy balance tower in the Upper Gunnison in that time, but also because it gives us variability in snow conditions and assess how the model handles that variability.
Thanks. And then there's also a question from Ethan regarding your modeling. What is the wind simulation you use in AWSM?
That's a great question. It's Wind Ninja. And I don't know that I could answer many questions about Wind Ninja. I would refer those to Scott Havens or somebody at the NWRC team, that they're the developers of AWSM.
Great. And it looks like the last question we have is for Sean, or maybe we have one more coming in. Is there any difference in the skill of rainfall-driven versus snowmelt-driven watersheds?
Yeah, so the way we set up the testing so far has been to build as much of an apples-to-apples comparison as reasonably possible with the existing system. And the existing operational PCR models do tend to be focused on snow data and using that as the basis for seasonal runoff projections, which is pretty much the standard across the, well, Western North America as a whole. But of course, it does have limitations, and those limitations are therefore propagated into the results from the hindcast testing and operational testing that we've done with the M4 system at the moment. If you use the same predictors and they're based on snow, then you're not going to do as well in rainfall, more rainfall influenced environments. That said, going forward, we're very interested in exploring a lot of different input predictor data sets beyond what has been conventionally used in operational WSF systems, which again tend to focus mostly on snow data. So that includes, of course, potentially improved snow data, remote sensing products, MODIS, ASO, what have you. Even SNODAS for that matter, iSnowball, all these things are on the table for us, but also things that go beyond snow. You know, because a substantial proportion of the spring summer runoff, depending on the basin, is not from snowmelt. So, you know, the kinds of things that Matthew's been working on with looking at seasonal climate models, things like that, which are, you know, projecting what's coming up rather than what's on the ground at the moment. Things like that should help quite a lot with improving forecasts in more rainfall dominated environments. But yeah, you know, it's just a general truth of water supply forecasting, the kind of seasonal scale forecasting in cold environments, is that the majority of that runoff comes from, and therefore the best predictor of what that runoff will be is snow and snow data. So that's how the system is set up at the moment. But again, we're looking to expand that a lot going forward.
Thanks, Sean. A follow-up for that. Would you consider using predictors that don't have fully physical explanations for their skill, so such as sea surface temperature or other variables?
One of the reasons this system is, you know, getting operational, you know, buy-in, stakeholder buy-in, user buy-in, is the fact that it is very much framed in terms of physical relationships, and that's you know, sort of classically been a criticism of AI. There's a lot of techniques that are emerging to kind of sidestep that. There are also a lot of ways that you can simply, choices you make when implementing an AI that facilitate geophysical interpretation. So using things that are non-physical as predictors kind of undermines that process. That said, sea surface temperature, the relationship that can have to water supply forecast is not non-physical. Those SSTs reflect climate processes that will affect runoff generation. So ENSO is an obvious example. A lot of the indices in ENSO reflect the actual dynamics of that ocean atmosphere circulation phenomenon, specifically equatorial Pacific SSTs. That's your index telling you what the ENSO condition, what the ENSO state currently is, and what, you know, due to thermal inertia and whatnot, will continue to be for some amount of time, you know, weeks, months going forward. And that gives genuine predictive skill. It's not great predictive skill, and it can backfire. So you have to be very tricky with that, but that actually does reflect a physical phenomenon.
Yeah, definitely. So looks like we have one final question for Lindsay. What are the different considerations for testing with either Vic or with Zuma?
Sarah, was that for me? Can you ask that again?
I think it was for Lindsay. If
Sorry.
Lindsay's speaking, we can't hear her, but if she's, not available, you could also take it.
I'll wait for Lindsay.
Yeah, if you want to take it, Andy, go ahead. Oh,
Can you ask the question again? Was it?
yes. So what are the different considerations for testing Vic versus Zuma?
Hi, am I back?
Oh,
Phone cut out, but go ahead, Andy.
Okay. I mean, I would just say that, you know, in implementing a water supply forecast model, you have the same kind of considerations across really a lot of modeling applications. I mean, you want to find a model that you can calibrate to have a high ability to reproduce stream flow, but also that gives you some confidence that it's getting there for the right reasons, that you're, you know, the processes that are really important for a seasonal prediction are well established in the model. I mean, I had a paper many years ago where we looked at whether you could take a sort of poorly calibrated model and get a decent forecast just through post-processing it, because even if the model is quite biased, it presumably knows the difference between a wet and a dry year. And that sort of works at a seasonal scale, but it breaks down once you start to get to finer and finer periods. And so, for instance, if you're looking at like a 2-week period when, or the shape of a seasonal runoff, and the model has a tendency toward early or late runoff, then you really can't restore that easily through post-processing. So, you know, it's that balance of the amount of skill you can get as well as the process kind of fidelity of the model. And then the last thing is just the computational, you know, efficiency or ease of the model. You know, we've seen with, as you get toward higher and higher complexity, you start to get into modeling situations where you really just don't have the ability to run enough calibration trials or ensembles or hindcast or long enough simulations to effectively create a water supply forecasting model. And so I think both Zuma and Vic have that. I think the National Water Model could have that if it were implemented in a kind of a lower resolution fashion for some of the processes. But that's certainly another consideration when you get to a forecasting application.
thanks, Andy. Lindsay, do you want to follow up on that?
Yeah, no, I think Andy covered it. I will say there are other efforts through other groups looking at the National Water Model, or at least Warf Hydros, and how to work with ASO data in that model as well.
Great, thanks. So now I'm going to hand it back over to Seth for some closing remarks.
Okay, I found the unmute button. So I just want to say thank you so much to Sarah for your moderation. Excellent. Thank you for your work on that, and all of our speakers for your presentations today. You know, as you can see, there was a variety of presentations here on models and data and things like that that can potentially inform the RFC's water supply forecast. And I think you can also see that, you know, some are, I think, very close potentially to making the case that those approaches could be incorporated right away. Others perhaps are going to take a little bit longer period of time. And also just want to point out that there's a lot of considerations for some of these approaches within the current operational paradigm as well that have some importance to consider. I think that is the task that is obviously difficult for us all in this basin to think about, is how can we incorporate some of the best and newest research and science on these topics into some of the procedures and practices that we have on the ground. And I just want to say, again, thank you to all of our presenters and Sarah for walking us through some opportunities that certainly were identified in the State of the Science report, as well as challenges that we'll continue to have some conversations about to try to ultimately achieve forecasts of water supply and understanding of the uncertainties in a better way. Also want to thank Keely Brooks for all of her organization for the webinar today and background work, as well as all of the members from our Colorado River Climate and Hydrology Work Group. Your support just continues to make these kinds of engagements very helpful and pushes our understanding of the issues of water supply and demand in the basin so much further along by having these kinds of conversations. So I'll just end by saying, thank you to all of our participants for joining us. We had about 100 folks join us today. So hopefully you were able to learn something, and definitely would like to say we hope you can join us next time. Like I said at the beginning of this call, this is just the first part of a 3-part webinar series that are exploring some of those challenges and opportunities from the State of the Science Report. Our next webinar is October 19th, and we'll be discussing prospects for advancing hydroclimatic prediction at seasonal and longer time scales. So we kind of extend the time period a little bit with our next presentation. And then lastly, we'll have a November 17th webinar on decision science. And something that I know many of us on the call are certainly interested in, this research category or area of research and how it might help make or inform various basin-wide management decisions and things like that. So definitely want you to try to register for these webinars if you haven't already. There's a link on the screen, and we're going to go ahead and put that link in the chat window too, so that you have that really easily to click on and register. So with that, I just want to say thank you everybody for your time today, and hope to see you on October 19th. Have a great day.
Thanks, Seth.
Yeah, thanks a lot, Seth.
Bye, folks.
Thanks. See you later.
Okay, I think I got the webinar link into the chat box, but we will conclude the webinar right now. Thanks, everybody.